Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 11, Lesson 4, Standard Deviation. By the end of this lesson, you'll be able to quantify and analyze the spread of data. And we'll learn what normal distribution is, what standard deviation is, and what variance is. For the model and discuss, we have two 10-day forecasts for two different cities, City A and City B. We can create a data display to observe the shape of the data and look at measures of center. So I think a histogram would be best. As we can see, we've got ranges of temperatures and we can calculate frequencies of each of those intervals. So for City A, here's the histogram. You can see that our interval is from 62 through 63 degrees up to 64. Then we have 64 through 65 or up to 66 degrees, and 66 through 67, and 68 through 69. And we've just calculated the frequencies for each day that falls within that temperature interval. And we did the same thing for City B with the same intervals. It's important that we have the same intervals when we are comparing different data displays. So if we look at City A, the shape of this data looks pretty symmetrical. And the shape of City B, we can see that it looks like it's skewed right. We have this outlier here on the right, and most of the data is over here in this interval. So City A is more evenly spread out because of that symmetrical shape. City B has that outlier, so it is skewed right. So for City B, the outlier, again, pulls the mean towards it, so the mean is going to be greater than the median value for City B. Example 1, interpret the variability of a data set. The markers of a certain brand of light bulbs claim that the average life of the bulb is 1,200 hours. So here is our mean. We could say that's X with the line over it. The lifespans in hours of a sample of brand A light bulbs are shown. How close to the claim were the light bulbs in this sample? Or how close is the data to the mean? So we have our data here, and we can make a histogram to represent that. Again, looking at intervals of lifespan. So we have our intervals here, okay, and we have calculated the frequencies of each of those intervals. And we can see the shape of our histogram to look at mean and measures of center. So our shape looks pretty symmetrical, and it's forming what is called a bell-shaped curve. So the data display shows that normal distribution, that symmetrical shape, and this is called a bell-shaped curve. When we have normal distribution, we refer to it as a bell-shaped curve. Okay? So most of the values are going to be distributed and clustered around the mean. Okay? And then as we move farther away from the mean, we have lower frequencies as we're farther away from the mean. When we have normal distribution, we can look at standard deviation. So again, we're still looking at the lifespan of these brand A light bulbs. Okay? And standard deviation has set percentages that fall within each standard deviation. A standard deviation is a certain amount of distance away from the mean. Okay, so if the mean is right here in the middle, one standard deviation can go to the right or be greater than the mean. One standard deviation could be to the left or less than the mean. And one standard deviation to either side of the mean constitutes 34%. So 34% on either side, that gives us a total of approximately 68% of the data that falls within one standard deviation, or one unit of standard deviation greater than or less than the mean. Two standard deviation then is just two of those distances away from the mean, and 13% of the data is farther out, but all together, so if I'm combining these two percentages on either side of the mean, then we're going to have 95% of the data that falls within two standard deviations from the mean. And the next 2.1% are in the next section, or 3 standard deviations away from the mean, again, to the right or to the left, plus 3 or minus 3. And if we add up all of those percentages, then the total amount of data that falls within 3 standard deviations is pretty close to 100, but not quite. About 99.7% of the data falls within 3 standard deviations. We still have this little group here that is even farther away than 3 standard deviations, but it's a small percentage. So again, you'll want to know these percentages. 68% of the data will be within 1 standard deviation, 95% will be within 2 standard deviations, and almost 100%, but not quite, 99.7% will be within 3 standard deviations. So the standard deviation for this particular data set is 75.5 hours. That means 1 standard deviation is 75.5. 2 standard deviations would be 75.5 plus 75.5. Since the mean is 1200, then if I go to the left and to the right of 1200 by 75.5, so here I'm going to draw 1200 in the middle. That's my mean. I can add 75.5 for 1 standard deviation, or I can subtract 75.5 for 1 standard deviation to the left of the mean. That's how we get these values. 1200 minus 75.5 would get us 1124.5 hours, and if I add 75.5, I get 1275.5 hours. Those are the boundaries, if you will, of 1 standard deviation away from the mean. And remember, if it's 1 standard deviation, we know that that's going to cover 68% of the data. So 68% of the light bulb surveys should fall within this interval of lifespan. So normal distribution, having bell curves is great for making predictions because we have these set standard deviations that we can make calculations and set percentages of data that fall within those standard deviations. What is the lifespan of light bulbs that are within 2 standard deviations and 3 standard deviations? So again, I'm taking my mean, 1200, and now instead of adding just 75.5 once, I'm going to add it twice. And then instead of just subtracting 75.5 once, I'm going to subtract it twice. Okay? And so for 2 standard deviations, we're going to get between 1,049 and 1,351 hours. Okay. And then for 3 standard deviations, we're going to do 75.5 times 3 plus or minus from 1200. And we would get an interval of 973.5 hours through 1,426.5 hours. So that's standard deviation, above the mean or below the mean. Example 2. The table shows the number of cars sold by an auto sales associate over an 8-week period. Okay, so we're looking at an 8-week period. We're not looking at their whole career as a car salesman. So we're just looking at a sample, a small selection of their total sales career. Here's the data we have. And we can find the variability by solving for the standard deviation for a sample. Again, this is a sample. It's not their whole career, it's just an 8-week period. And so this is the formula for standard deviation. Okay, a couple of symbols to note. This epsilon symbol here stands for the sum of whatever comes in the parentheses. We already know what's in the parentheses, the x value, the data point, minus the mean, but now we're going to square it. Similar to what we did with mean absolute deviation, where we took the absolute value of the difference between the data and the mean, but when we do standard deviation, we're going to square the values. And then we're going to divide by n minus 1. N represents the number of data points, and then we take the square root of that. Since we squared our difference from the mean, our deviations, we need to then take the square root, undo it when we're calculating standard deviation. Now, the reason why we divide by n minus 1 is because we are doing a sample size, and we're going to talk about that a little bit later. So here's the formula to calculate standard deviation. Why would we use standard deviation instead of mean absolute deviation? Well, again, if we have normal distribution, if we have that bell-shaped curve, we can calculate standard deviation. So this we will use for normal distribution. It's great for predicting, and we can also take out big effects of outliers. Okay, so we will use standard deviation when we have normal distribution. Step 1, find the mean of the data. So we can do that by adding up all of the data points and then dividing by the number of data points. Okay, so remember x with the line represents the mean, and if we add all of them up and then divide by the number of data points, 1, 2, 3, 4, 5, 6, 7, 8, we would get 17. Okay, and then we can fill out our table. So here we have our data points from the data. The next row is just the mean. It's going to be the same all the way through. We find the difference of the mean. We take the first row and subtract the second row. And then, since we're doing standard deviation, we will square all of those deviations, or the differences from the mean. Okay? So you can see how we filled out the table. We just did 18 minus 17 is 1, and then we square 1 and we get 1. We did 25 minus 17, we get 8. Then we squared 8 and we get 64. And so on to fill out the table. Okay, so since we are squaring the difference, this gets rid of our negative values, or our values that go to the left of our mean. When we're calculating distance, distance is always positive. So that's why we square the deviations. After we've calculated that, we can type in our values and calculate the variance. So the variance is like the step right before you take the square root of the standard deviation formula. The variance of a population is noted by this, sigma squared, or sometimes just s squared, okay? And it measures the differences between the data values and the mean. So when we are finding the variance of a sample, again, smaller data size, then we're going to use s squared. So you can just think s sample s squared. And then n provides too small of an estimate, so then we're just going to divide by n minus 1. Okay, so there is a reason why we divide by n minus 1 when we're talking about a sample, because we don't want our standard deviation to be too off. So since we're doing a smaller data set, we're going to divide by n minus 1. Okay, so we get a slightly bigger number. Again, instead of dividing by 8, I'm going to divide by 7. So dividing by a smaller number gives me a bigger total, a bigger quotient. This helps us get a closer representation of the true population, since we're just looking at a sample. Okay, that's a lot of theory about why. You can just remember, if you're talking about a sample, you do n minus 1. Okay, so you can put in here, this is just your sum of the squares. So this is the bottom row from our table, the sum of the squares. And then we divide by n minus 1. We had 8 data points, so we divide by 7. And then before we take the square root, we get our variance. So s squared is our variance, 17.71. Okay, the last step to finding standard deviation for example 2, we have the variance. We calculated to be 17.71. Now we need to take the square root. That is the last step in finding standard deviation. So the square root of 17.71 is approximately 4.21. Since we're talking about car sales, we can't sell a decimal or a fraction of a car, so we're going to round our standard deviation to approximately 4 cars. So our standard deviation is about 4 cars. The mean was about 17 cars. If I'm looking at 1 standard deviation away from the mean, which would account for 68% of the data, again, we're going to take our mean and we're going to subtract 1 standard deviation, or we will add 1 standard deviation. And that's how we get the range of 13 to 21 cars that would be sold within 1 standard deviation of our mean. So for the try it, we're going to do the same thing. It's a separate 8-week period, so we're going to calculate the mean and then the standard deviation. So calculating the mean, adding up all the data points, and dividing by the number of data points, we would get our mean of 16.5. Okay, we have 8 data points, again, 8 weeks. Then we're going to calculate the difference of the mean, difference from the mean, the deviations, and then we will square them. So I'm just going to, we know the mean is 16.5. Okay, that's the same for all of them. And then I'm going to skip the step where we just write the difference from the mean. I'm just going to write the squared difference from the mean. So 12 minus 16.5 and then squared, we would get 20.25. 14 minus 16.5 and then squared, we would get 6.25. 29 minus 16.5 and then squared, 156.25. 10 minus 16.5 and then squared is 42.25. 17 minus 16.5 and then squared, not much difference, 0.25. 16 minus 16.5, same difference. So that again is going to be 0.25 since we squared it, even though the difference is in the opposite direction. 18 minus 16.5 and then squared would be 2.25. And 16 we know is another 0.25. Okay, add all of those up. Since this is sample data, we are not looking at the whole career of the auto salesman. We're just looking at a sample of 8 weeks. So we're going to do n minus 1, which would be 7. So we're going to divide by n minus 1. That would give us a variance of, a sample variance of 32.5714 approximately. There's some more decimals after that. And then to find the standard deviation, we take the square root of that number. It's approximately 5.7, or we would round up about 6 cars. So this 8-week period had more variance. Instead of having a standard deviation of 4 cars, we have a standard deviation of 6 cars. So more variance in this 8-week period. Okay, for example 3, what are the mean and standard deviation for this data set? This data set represents the points scored by a football team during their regular season. So how many games do we have? 2, 4, 6, 8, 10, 12. We have 12. This is a typo. It should be dividing by 12. Okay, so finding the mean, we add up the data points and then divide by the number of data points, which is 12, gives us a mean of approximately 16.8. Then we're going to use our standard deviation formula. Now, this is their whole football season. So since it is the whole football season, we are not looking at sample data. We are now going to be using our sigma squared for variance because we're looking at the whole population. Okay, this is the full population data, so we're going to be dividing by n now instead of dividing by n minus 1. Otherwise, the math is still the same. So we subtract the data point, 24 minus the mean, and then square it, and we do that for all of the data points, okay? And we're dividing by 12, the number of data points, and we get a variance of approximately 53.8. Okay. And then our last step, of course, to find the standard deviation is to take the square root of the variance. So the square root of 53.8 is approximately 7.3. So our standard deviation for this population data set is 7.3. Now, again, we're talking about points scored. You can't score a fraction of a point. So we can round, and we can say from 17, our mean is approximately 17. Okay, and if I subtracted 7.3, and then I added 7.3, okay, and then we would round to adjust for the fraction of points, we would get a range of between 10 and 25 points. That would account for 68% of their games. So that's within one standard deviation of the mean. Again, we rounded the mean up to 17, okay, since we're talking about points scored in a football game. For example 2, we're practicing doing this on a graphing calculator. So the cool thing about our graphing calculators is they can do a lot of this work for us. So we've seen this before when we were looking at one variable statistics with interquartile ranges and our box plots. So it's the same procedure. We're going to type in our data using our stat calc feature. So go into stat and edit, enter your list of data points. You can put them into L1. Now, since we're just looking at one variable data, we just have data for our x variable, we are going to use our one variable statistics. So after you type in your list, then you're going to go back to stat and hit the calculate feature. So go over to stat calc and hit number 1 for one variable statistics, and then enter, and it will pull up this screen here. Okay. And we can see, we know what these symbols mean. So our x with the line is our mean. Our mean is approximately 15.9. Then here we have 2 versions of standard deviation. We have the one with the symbol S, that's for sample data, and we have the one with the sigma circle with a hat, that is for population data. Since we're looking at the whole football season, we're going to use the population data, the standard deviation for population. So our standard deviation is 7.3, approximately 7.3, okay? So again, we could take our mean, 15.9, and one standard deviation would be subtracting 7.3 or adding 7.3 to be within one standard deviation of the mean. For the try it, it's asking for data within 95% or 95% of the total data. Well, if we remember our percentages, we know that this falls within 2 standard deviations. So we're going to just do the math, calculating 2 standard deviations away from the mean. So our mean was 15.9 points, and we're going to subtract 2 times the standard deviation of 7.3, and then we're going to add 2 times the standard deviation of 7.3. This gets us to be 1.3 and 30.5. And again, since we're talking about points scored, we're going to round up. So we would go between 2 to 31 points scored would be within 2 standard deviations, or 95% of the regular games would score in this range. Example 4, application, comparing data sets using standard deviation. So we have 2 histograms we're going to compare. They show the lifespans of a sample of light bulbs from 2 different companies. The first histogram is for brand A, and we can see the mean is 1,200 hours, okay, and the standard deviation they gave us is 75.5. If I'm looking at the shape of this distribution, it looks like normal distribution. Okay, so we have that bell curve shape for brand A. For company B, or brand B, we have a mean of 1,200 again. The standard deviation is much higher, 90.25 hours. Well, we can see that the shape of our data is skewed right. So it makes sense that we have more variation. Okay? We have bigger spread because of those outliers off to the right. So both brands of light bulbs have the average or mean of 1,200 hours. The standard deviation for data set for brand A is less than the standard deviation, again, because we had that normal distribution in brand A. Okay, so there's less variability with brand A. Okay, less variability. Our data is going to be closer to the mean. For brand B, our data will be farther away from the mean. One standard deviation is a lot farther away from the mean. So brand B is not going to be as reliable. There is more variability with brand B. So if you want to have a reliable light bulb, you know you want to get as close to 1,200 hours as possible, you should buy brand A. So for company C, we have a mean of 1,250 hours, and a standard deviation of 83. Let's compare this to brand A and B. It does have a higher mean, but what does the standard deviation look like? So one standard deviation away, I'm going to subtract 83, or I'm going to add 83. So 1,250 minus 83 would get us to 1,167. 1,250 plus 83 would get us to 1,333. And comparing that to brand A and B, brand C has a higher mean. It has a higher mean. And its standard deviation, I'm just going to use S for standard deviation. It's greater than brand A, but it is less than brand B. All right, you've made it to the concept summary. Make sure to come back for our last lesson in topic 11,